In reality, you have a big chunk of rewrite rules that you want to apply at some don't want to store it multiple times for efficiency reasons, and that's more relevant for bigger terms, but so we store it just once and then reference it multiple times. Cool. And now what we just do is we take any rewrite that we have and just apply it in the e-graph. Let's say the first rule we have is a multiplication by 2 can be replaced by a shift by 1, and we see that we have a times 2 in the e-graph, so we want to apply it there. And when we've done this, we see that the a times 2 is not actually gone, so it's not a greedy rewrite, but we've rather added an equivalent way of saying, okay, this is also equivalent to a shift 1. So by this rule, we've now put both of these things, both of these nodes, into an equivalence class or e-class that now represents both of them together, which means from now on we will not differentiate between a times 2 and a shift 1, and they will just be considered the same, which makes this more compact. Cool. And now we really just do the same process over and over again, apply a rule, improve, apply a rule, etc. And in the end, we'll see that the initial term that we put in there, represented by this division operator, is now actually in the same equivalence class as A, which means we're done. We've actually done the optimization. Perfect. Now, the problem is this gets a bit harder when you have bound variables in your language, right? So a bound variable is really just, you have a binder, like a lambda, for example, that's introducing a local variable like x, and then this x is really, the meaning of x makes only sense in the body of that binder. And so the important property for bound variables is that the names you actually choose for the variables don't ever really matter. So you can always just rename them, and we'll see that this is something that e-graphs really struggle to understand to some extent. And I want to show this as an example. Consider the two terms, f of xy and f of x prime y prime, which are pretty much the same, except that there are different names of variables in them, right? So structurally, these are really the same terms. You can kind of, if you analyze them, you'll see you'll make the same conclusions, just that the conclusion will have x prime instead of x and y prime instead of y. So whatever you know about f of x and y, you can translate that knowledge directly over to f of x prime y prime, and it's really structurally the same thing. But when we see that we store this in an e-graph, we'll see how it's actually stored separately. So this knowledge that these are structurally the same term is not really exploited. So we actually pay with kind of storing it twice, storing a copy, and also analyzing it twice and doing operations twice on it, which is costly, and we don't want to do that. And even worse, some of the rewrite rules we might apply might run into naming collisions, which then require us to actually do renamings. And as we've seen before, these renamings are exactly what creates copies, and that blows up the e-graph in size. That's unfortunate. So the typical trick to avoid this is to just say, okay, let's not do names, let's just do the Bruijn indices, then we don't have all of these problems, hopefully. And just a quick reminder how the Bruijn indices work. So we want a way to reference from the variable to the binder, right? That's the whole job of the Bruijn indices. Typically, we do this just by names, by just saying, well, the variable the variable y is representing, is pointing to the binder y, same thing for x. But in the Bruijn, because we don't want to have names, we rather say we just count outwards. So that means because y is the innermost binder, it's the Bruijn index 1, and because x is one more outside, we have to skip one more binder, it's the Bruijn index 2. So this term in the Bruijn notation looks like this, and wonderful, we've gotten rid of all the names. Perfect. But now, because the Bruijn index just count outwards the number of binders, if the number of binders changes because the rewrite rule is adding or removing one, we actually have to correct that binder. Sorry, we have to correct that Bruijn index, right? So we have a rule that adds or removes a binder. The Bruijn index needs to be shifted to actually correct for that offset. Typical example for this is beta reduction. That's eliminating the function binder, the lambda, that's actually being called. So you're kind of off by 1 if you don't correct the index now. And that's a problem because this index shifting, this correcting the Bruijn index, is again creating a copy because it's really similar to a variable rename that we've just seen before. So it doesn't really solve the problem that we had. And that's the key problem. If you repeatedly do index shifting because of the rules, you explode the e-graphs the same way, and it looks like this. That's the problem we want to solve. All right, now I want to see how we solve that. We solve e-graphs. the very basic idea is we want to represent terms that are just equal up to renaming variables by the same parameterized e-class. And we want to parameterize these e-classes by the free variables that we have in them. And we want to make an example, like the same example we've seen before, for this conventional e-graph, which has this kind of copy of f of x and y and f of x prime y prime, we've just seen before. And the first thing we want to do is that these 4 variables that we have at the bottom, they're really structurally the same. So we want to represent by one object, by one parameterized e-class, which looks like this. Right. And as you can see, this parameterized e-class now has a header where we say this e-class actually depends on a variable v that you have to plug in. This is what we call a slot. That's why it's slotted e-graphs. So you have to kind of, whenever you reference this, you have to say what v is supposed to mean, and that differentiates between the different kinds of variable, x, y, x prime, y prime. Right, and this is just the general variable e-node that's supposed to mean, well, I am the variable v. Right, and now, because we want to also represent f of x and y, we again have to convert that to a parameterized e-class, which now, because it has 2 free variables, x and y, should also have 2 parameters. We arbitrarily choose the names a and b, doesn't matter, and we get this e-class. So this, again, represents f of x and y and f of x prime y prime. It's just one e-node, the f e-node, and because both of children of f are just variables, we have to point twice to the variable e-class. But in order to differentiate which variable we actually want there, we have to invoke the variable e-class by saying what v is. So in the first case, we say, well, we want the variable a on the left, and we want the variable b on the right. This is what these annotations on the edges mean, right? This has to match up with the parameters here in the variable e-class. Cool. And now, in order to make the intuition for that a bit more clear, I want to get back to what a conventional e-class is, first of all. So a conventional e-class really just is an equivalence class of terms. So it's supposed to represent a bunch of terms that are just equal. And this is slightly different from a slotted e-class because there's this extra level of parameterization. So what a slotted e-class is really a function that takes in some names, a, b, and then gives back an equivalence class using only these names. This means that if you call this with different inputs, you actually generate different equivalence classes, and this is kind of automatically spanning up infinitely many different equivalence classes. So something that would need to store manually otherwise, and is now kind of generally characterized. Cool. Now we can look into some more examples and some more features and challenges of slotted e-graphs, because there's a couple of interesting edge cases. So I want to first of all, start with binders. And I will start with the identity function lambda calculus as the kind of simplest canonical example, which looks like this if you draw it in a slotted graph. So you already know the bottom thing, that's the variable class, because we want a variable. But the new thing is this thing, which is a lambda binder. What it's doing is it's introducing a local variable, a local slot, x, and then because the body of the lambda is also just the variable x, we use this slot to then invoke the variable e-class with it. And that's pretty much already everything. One thing to point out is that this e-class does not depend on x as a parameter because we don't want lambda x dot x and lambda y dot y to open different equivalence classes, right? So this is supposed to be the same thing, alpha equivalence. So if you don't have the parameter, what this really means is that it's automatically covering all the renaming versions all at once. Because it's like if you change the name, it's not supposed to open a different equivalence class. So they're all covered in there automatically. And we'll see another case where this is going to be interesting in the next slide, which is the case where we multiply variables by 0, which is, well, we know what happens then. Whenever we multiply something by 0, it's going to be 0. So what we want to do is we want to merge the 0 e-class at the bottom with the x times 0 at the top, because they're equal, right? We just proved they're equal, so we should merge the classes. But it's kind of weird because x times 0 does depend on the parameter x, but 0 does not. So we have to kind of make a choice now. Should the final class actually depend on x or not? And we argue with that because x times 0 is equal to 0. It should not actually depend on x, and it will look like this. But now you might be a bit confused because the x is still there. Like the x is now nowhere defined, it just floats around there. But this is actually kind of the same we've seen in the previous slide, where if the slot is not part of the parameter list, what it really just means is all the renamings covered in one. So because whatever you multiply with 0, it's 0, this is automatically covering all the renamings of x times 0, which makes a lot of sense, I think. And yeah, so that's that. Now we come to the third feature, or the third interesting case, which is which is the case where we have the addition of two variables, two different variables. And well, we know if we have a plus b, we know that it's equal to b plus a. There's this symmetry. And so what this means, we want to merge the kind of the E-class representing a plus b with the E-class representing b plus a. But the problem is, well, they're already the same E-class, right? The generalized E-class is kind of covering both of them. So how do we merge the class with itself? What we kind of want to say is we want to say that this E-class should be equal to itself if you change the order of parameters. That's what we want to express somehow. And so we do exactly this. And we have this permutation group at the top, which is sometimes there, and often it's just one element. But this really just means that however you call this, whether you call this with AB or with BA, it's the same equivalence class that gets generated. So it's not actually opening different classes. So again, this class is really just a function, and then it has both versions, A plus B and B plus A, in them now. Cool. Now I want to come to the evaluation. We have 3 case studies, and I want to first of all start with the Rice array language. On the left side, you can see the grammar for the language, and it's pretty much lambda calculus. We just have a bunch of symbols that have kind of special meaning, but it's pretty much lambda calculus. On the right side, you can see how this looks in the implementation, and I think it's quite convenient. You can basically just translate the constructor from the left and put it to the right. One thing to point out is that, yeah, we have a special bind thing to say when you want to actually introduce a binder. But otherwise, this is like very similar to what egg is doing, and yeah, not much new, but it's quite convenient to define binders. Same thing for rewrite rules, where if you have here the LaTeX version of the rewrite rules, you can more or less kind of just write them the same way. Here you can, for example, define eta reduction. You have to be a bit more explicit with the kind of function application, because kind of function application is implicit in lambda calculus, so you have to write app here, which is maybe a bit annoying, but I think that's okay. And yeah, you can also do the side conditions, as you can see at the bottom. Right. And even for rules that are a bit more complicated, because they introduce a lambda, like you can see here, you can just write it, and it just works. So there's no problems like, oh, I have to shift the indices, or what variable do I actually choose? It doesn't matter. You just invent the variable, and it works. You don't have to think about it, and I think that's quite convenient. Cool. But now let's actually look at some real data. So at the top, you can see kind of a family of rewrite problems, which you can kind of blow up by making the number of function parameters longer and longer. And at the x-axis, we see exactly that, kind of the number of function parameters. And on the y-axis, we can see the time and memory that egg and slotted take to solve this problem. And egg is using the Bruijn indices in this case. And yeah, we can see that for this particular case, slotted does not really care if the number of function parameters is growing. And it's really hard on egg de Bruijn, because this particular problem is generating a lot of index shifts that are really hard to handle if you use the Bruijn. Yeah, and so we see in this case at least that's very, very efficient, very compact to use slotted. Yeah, let's get to a more real-world example where we have kind of more bigger, interesting programs from the STQL case study, which comes from database theory. And here on the left side, we see a bunch of examples, a bunch of programs we want to optimize. And you can always see in the white, we have the egg, the Bruijn baseline, and in gray, we have the slotted one. And the first thing I want to point out is that the number of iterations for slotted is consistently lower, right? And that makes sense because egg de Bruijn is investing a lot of iterations just to shift indices, which is happening a lot, and yeah, well, cost iterations to do. And so because this is just not happening, yeah, you just can do stuff in few iterations. Equivalently, you can also see that the number of nodes in E-classes is much lower in some cases, or it's always lower, but sometimes much lower, which makes sense because we kind of represent different things that are equal after renaming now in one. So all these different copies are now compacted in one in the slotted implementation. Right, but you can still see in some cases that we still have slightly higher memory consumption than egg. And that makes sense because we pay some extra by having these slot annotations everywhere, right? That's an extra level of parameterization that costs stuff. You have to actually, that's an interaction you have to pay for. And if you're not getting something out of it because the de Bruijn is, in this case, not problematic, you're not winning anything. But you can also see that in some cases it is very much worth it. And you can get an up to 50x improvement on the memory cost. And in some cases, even, we do saturate with a rather small and efficient graph, whereas the baseline with the Bruijn is kind of getting bigger and bigger, and it's seemingly not going anywhere. Cool. Then the last case study, which is a quality saturation-based lean tactic that has a slotted and an egg backend. And yeah, what we can see here is that the slotted implementation tends to produce shorter proofs because, again, we don't have to do index shifting. And that's really something that seems to be the majority of the proofs if we have a lot of binders. And also, we have found a fancy example where we terminate in 1 second, and it takes a lot of time to not solve this problem, actually, which I think is very cool to have found that. Cool. Then finally, I would like to invite you to have a look at the paper, where we, first of all, define the slotted egraph data structure and talk about its algorithms a bit. But also what we did is we formalized a notion of congruence modular renaming, because egraphs normally work with congruence, and we need to extend this to understand kind of the notion of variables that we're interested in, modular renaming. And right, finally we have the case studies in more depth, and yeah, that's pretty much it. There's the paper and the implementation on GitHub. Have a look, and yeah, I'd like to hear your thoughts, so that's my mail. Thanks.
Questions? Someone?
I'm Michel from GIA, and we are using. Thank you for your fantastic talk. We are currently using egg in our production code base, and it has ad hoc treatment of bound variables. So I am really definitely give a try to it. And one question is that does thread egraph suppose relational e-matching or egraph?
Okay, so the kind of e-matching that we're using is the question?
Pardon?
The question is which kind of e-matching we're using?
Yeah.
Yeah, so we're really using kind of the most boring e-matching you can think of, that we just kind of directly convert to slotted. So it's really normal top-down e-matching without any fancy optimizations. So the e-matching is not very competitive, but I think Nate is actually implementing a better version right now that's based on the 1 from egg, but it's not using the relational yet. So not the typical database egg-log style. It's not that yet.
Is it on the I couldn't get it. So is it possible with this framework?
I think it should be, but I don't know. Like I didn't implement it yet. So
but not bad. Could be.
I don't see the problem. I think it should be possible, but yeah, we'll have to see.
Okay, thanks.
Yeah.
Thank you. Very exciting work. So I wonder if you have comments on, like you said, like the paper will mention about like imaging and rebuilding, but I wonder if you have intuition for example, if the imaging for the solitary egraph is more expensive, and as for rebuilding, I can imagine like rebuilding will involve some, you need to find correspondence between the variable names between 2 e-classes to merge them, and I can imagine it's a delicate procedure, like it may be incomplete. I just want to know like what's your intuition on the rest of the operations of the egraphs.
Yeah, I see. So I feel like what's happening is that you can basically take the normal algorithms, but you have to kind of always do a bit more in the kind of inside when you always have to kind of, and then multiply this renaming on top of it to actually get the names right. But I feel like the structure of the overall algorithm really stays the same. And like it's basically the same algorithms, but because you've mentioned rebuilding, there's one more notion where you have to kind of think of, like when you notice that a slot is redundant, which we've seen in the case where x times 0 equals 0, that you have to kind of propagate this upwards a bit. So there's kind of multiple notions of rebuilding now, because you're not only propagating equalities, but also you have to propagate that you're not depending on some parameter anymore. So kind of there's some new kinds of propagations happening in rebuilding, but I think algorithmically it doesn't really change that much. So
I see. So maybe one very specific example, say if you have variables AB, FAB, and BA, FBA, like would you merge these two together during rebuilding? Because like it seems one is an alpha renaming of the other.
So generally, what we do is we have this kind of shape computation where when we have f of AB and f of BA, these will just be computed to f01 and f01, both of them. And then so we kind of split the names from it and give them a naming independent representation. And we just, like that's before rebuilding, that's happening all the time. So whenever we put something into the egraph, the slotted egraph, we will always get rid of the names first and have a naming independent representation that's kind of enumerating where the names were, and then having separate with that the renaming. So this is really something that's happening kind of very early in the process before rebuilding. Separate it.
I see. Thanks.
All right. I think we had a very exciting talk, so thank you very much, Rudi.
Thanks.